An organization produces two products, A and B. Profit on these products are given as 350 and 450. Raw material requirements for product A are given like this. Raw material 1 requirement is 50 units per unit of product A, and raw material 2 requirement is 30 units per unit of product A. Similarly, for product B, the raw material requirements are 30 and 60 respectively. Availability data is given. We have to find out the product mix, that is the quantity of product A which we need to produce and quantity of product B which we need to produce, so that the profit is maximum and we operate within the resources available to us. We have solved this question in earlier video using the graphical method. Now we will try to solve it using simplex method. But first task is to get the initial basic feasible solution table. So in this video we will be focusing on getting an initial basic feasible solution table. When you do the linear programming formulation, the objective is to maximize the profit, which is given by this expression P equal to 350x plus 450y. Subject to the constraint 50x plus 30y less than equal to 1500 and 30x plus 60y less than equal to 1800. The decision variables x and y both are greater than equal to 0. It may be useful to recall that this amount 350 is the profit per unit of product A and 450 is the profit per unit on product B. X and Y are quantity of product A and B to be produced respectively. So they are the decision variables. In the constraints, the left hand side expression, that is 50x plus 30y, is the consumption of raw material 1. 30x plus 60y is the consumption of raw material 2. Consumptions should be lesser than equal to availability. So that's why 50x plus 30y should be less than equal to 1500 and 30x plus 60y should be less than equal to 1800. We aim to prepare initial basic feasible solution table in this video. For the linear program where the objective function is to maximize 350x plus 450y, subject to the constraints 50x plus 30y less than equal to 1500 and 30x plus 60y less than equal to 1800, x and y both greater than equal to 0. We have seen in the graphical method that first we go for the feasible solution space and then within that we try to find out the optimum solution. In the simplex method also the approach is similar. First we find out a feasible solution table and then we will keep on improving on the objective function value. So first we rewrite our linear program. The objective function, we will try to have an expression for it and we write P, bring right hand side values of the objective function on the left hand side. So P minus 350x minus 450y, and then for the constraints subject to these two technical constraints, they are less than equal to type, we need to convert them to equal to. So we can do it like this: 50x plus 30y, this is less than equal to 1500, So if we add something to this, if we add something to 50x plus 30y, then that will become equal to 1500. So we add a variable s1 and we say that this is equal to 1500. Similarly, for the second constant, it is 30x plus 60y, and since this constant 2 is less than equal to type, so we will add another variable here s2, that is equal to 1800. X greater than equal to 0, y greater than equal to 0. Actually, the simplex method works similar to the Gauss elimination method while solving the simultaneous equations. In Gauss elimination method, while solving simultaneous equations, you pick a variable and you do some elementary row operations to eliminate that variable from all equations except one, and that way it helps you in finding out the value of that variable. Here we have a concept of basic variable. A basic variable is such a variable which is present in only one equation and it is not present in any other equation. The equation in which it is present, the coefficient should be plus 1. So from the constants, that is from these two equations, we will try to find out basic variable. From each of the constant, we should get one basic variable each. The basic variable should be present in only that equation and not present in any other. Also, the coefficient should be plus 1. If you look at this equation, you find that s1 is the variable which is present only in this equation and not present anywhere else. The coefficient of this is plus 1. So s1 can be taken as a basic variable. Similarly, from the second equation too, you get s2 as a basic variable because it is present only in this equation. You don't see s2 in the first raw material equation or in the objective function line. So s2 is a candidate for basic variable and its coefficient is plus 1. So s2 can be taken as basic variable from the second constant. You notice that if the constants are less than equal to type, as you see here, since you are adding some variable like s1 and s2 to make the constants equal here to get the equation form, you will notice that s1, s2 or such kind of variables which you are introducing to convert and less than equal to equal to, these variables will become basic variable. The problem comes when the constant is greater than equal to type or equal to type. We will handle those situations in another example later on. Let us prepare the table now. For preparing the table, you write all the variables which are used in this problem. So the variables which are used are p, x, y, s1, s2, and we have something like right hand side values. So we write RHS, that represents right hand side values. And we will have rows in this table. The first row will be for the objective function. So we have p row, and then we have rows for the basic variables. we have two technical constants, so two basic variables, and we have already identified that S1 and S2 are basic variables. So we write here S1 and S2. Filling this table is quite easy. Simply take the coefficients from these equations and put that in the table. So if we look at the P line, the coefficient of P in P line, we are looking at this line, P line. So coefficient of P in P line is 1. You can see the coefficient of P here as 1. Coefficient of X in P line will be written here. So coefficient of X in P line is minus 350. So we write minus 350. Same way for Y, the coefficient is minus 450. Coefficient of S1 in P line is 0. As you can see, S1 is not present there. Coefficient of S2 in P line is 0. Right hand side there is nothing, 0. For S1 row, look into the S1 equation, which is this one, 50x plus 30y plus S1. Here you find that coefficient of P in S1 line is 0. Coefficient of X in S1 line is here, that is 50. So we write 50. Coefficient of Y in S1 line is this, and coefficient of Y is 30. So we write that here, 30. Then coefficient of S1 is 1, coefficient of S2 is 0, and the right hand side value is 1500. Coefficient of X in S2 line, that is coefficient of X in S2 line, that is 30. So we write coefficient of X is 30. Here coefficient of Y is 60. Coefficient of S1 in S2 line is 0. Coefficient of S2 in S2 line is 1. Right hand side value is 1800. And we forgot to put the value here. So coefficient of P in S2 line, that is also 0 because P is not present in S2 line. So this is the initial basic feasible solution table. This is feasible because right hand side values are non-negative, and basic, you have this as basis. Best way to understand basis is to understand that this is something like storeroom, and at the initial stage you have only the raw materials in the storeroom, and there is no product right now. If you read this table, that is again important, that we should be able to read the simplex table. So reading is, you take the left hand side, that is you have P, S1 and S2, and their values are given by the right hand side values. So you can say that this initial basic feasible solution table right now tells that P is equal to 0, S1 is equal to 1500, S2 is equal to 1800, S1, you can see right hand side value is 1500, same way S2, right hand side value is 1800, and those variables which are not there in the basis, they are 0. So you also notice that X is not there in the basis, so that is equal to 0. y is also not there in the basis, so it is equal to 0. It means that at this moment we are not producing anything of product A, so x is equal to 0. Same way we are not producing product B, so y is equal to 0. If you try to understand what S1 and S2 represents, you see 50x plus 30y is the consumption of raw material 1 and 1500 is the availability of raw material 1. So S1 is equal to 1500 minus 50x minus 30y. Basically S1 is the quantity of raw material 1 unutilized. So you can say that S1 is the quantity of raw material 1 available. Same way quantity of raw material 2 unutilized, that is being given by S2. So at this stage S1 is equal to 1500, that is entire raw material 1 has not been utilized, and same way S2 is equal to 1800, entire raw material 2 has not been utilized. Profit is equal to 0. This table tells you about the present store where raw material 1 is available in 1500 quantity, raw material 2 is there in 1800 quantity, product A and product B are not there, and profit is 0. This option is obviously feasible because none of the constraints are getting violated. Thus we get the initial basic feasible solution table. This table is initial basic feasible solution table. This may not be optimum, and for that the check is in the objective function line. If you get any negative value, as you are seeing minus 450 and minus 350, that indicates that the objective function value, which is 0 right now, that can be improved. You know that 350 and 450 are profits on product A and product B. So it is possible to increase the present profit value from 0, because if you produce product B, which is more profitable, 450, or you produce product A, which is having profit 350, in both the cases profit will improve. But we obviously prefer to produce such product which is more profitable. So maybe that we would like to produce product B and improve the profit, and to get the impact of that we will have to do some iteration. So the simplex iteration we will be doing in the next video. Initial basic feasible solution table we are getting like this.